right, welcome back everybody to the second day of the ASF NISAR Community Workshop, Part 2, Mapping Change with SAR Imagery. Hey Jackie, if you could, yeah, thanks. So all of the slides for this workshop are available for you to take a look at, and I'm going to paste the link here in chat. Ooh, get the wrong thing saved. Hang on 1 second here. All right, so this link is coming in chat. All right, so here's the link to the slides, and now if you could head on to the next, thanks. And so for our second day here, we are going to start with an introduction to interpreting SAR with Jacqueline Smale, and then Heidi Christensen is going to pick up with surface water mapping and log difference. Then we're going to take a short 15-minute break, which we can also use as an opportunity to help anybody who doesn't have all of the access and environment setup that they need. We can spend some time during that break if anybody needs a hand getting ready for the next portion of the workshop, which is RTC-based landslide detection with Dr. Forrest Williams, which will involve actually running through a Jupyter notebook. And then we have a half an hour at the end of the day for a wrap up in a Q&A. So with that, if you can head to the next slide and start presenting, Jackie. Thanks.
Awesome. Thank you so much, Alex. Yeah, so this section, we're going to talk about interpreting SAR imagery. So building off of what Heidi discussed yesterday and taking what we know about the concepts of SAR and applying them to interpretation. So again, as Heidi discussed yesterday, we can exploit sensor and target characteristics to know more about our area of interest. Target characteristics such as roughness and moisture results in different amounts of reflection and scattering, which will return different amounts of backscatter. So again, reviewing what we talked about yesterday, here are some schematics of example for radar backscatter for different features on the ground. And moving from left to right in this slide, we can see some different schematics of different reflections and scattering and what an image would look like with that type of scattering. So on the leftmost hand, there we go. The least amount of backscatter would occur with a flat area in which there's specular scattering. Here, the signal will be hitting a flat surface, such as a lake or road, and all of that reflection or all of that signal will be reflected away from the sensor, and there will be very little, if not any, backscatter from that area. So it'll turn really, really dark. So as you can see, here's a lake, and there's nothing really coming back towards the sensor, and it comes up very dark. Next to it on the right is an example of diffuse scattering, in which the signal is hitting something a little rough, and that signal is being scattered in all directions. So when it's scattered in all directions, some will be returned towards the sensor, just because that is a direction to go. But at the end of the day, not a lot of backscatter will be put or reflected or scattered towards the sensor, so it will show up relatively dark. So here's an example of a low vegetated area in which there's some backscattered returned to the sensor, but really very little. Next to that is an example of volume scattering, in which there is scattering due to complex interactions with more than one surface. So for example, here there's a canopy and the signal is hitting that canopy and just getting scattered in all directions. So we'll see higher returns, but in the process, there will be depolarization, which we'll talk about later. But that will show up as a little bit lighter than the diffuse scattering because there'll be more directing it back towards the sensor. And then finally, on the right-hand side, where we would expect to see the most backscatter is a dihedral reflection, in which the signal hits a flat surface and bounces off of an object such as a building or a tree trunk and is directed back towards the sensor. So here you can see there's these buildings and urban environment, and it comes up super bright. All right. So That being said, what we're going to talk about now is how we can use the sensor characteristics to better target those target characteristics. So what I'm going to talk about is the polarization of the signal and the wavelength of the SAR signal. So polarization, the electromagnetic waves that are transmitted and received by the sensor can be measured in two polarizations, traveling along a horizontal or vertical plane. So when there's a co-polarized signal, that means that SAR is transmitting and receiving in the same polarization. For example, HH would be transmitting and receiving in that horizontal polarization. On the other hand, there's cross polarization, in which the sensor is transmitting and receiving in perpendicular polarity. It's hard to say. So, for example, transmission. And the reason that's important is because the radar interaction with the surface depends, it will return differently those polarizations. So V, for example, returns the most, or like has the most scattering for rough surfaces, in which water, bare soils, and roads, that's where the most scattering will occur for the VV polarization. For HH polarization, double band scattering will produce the most scattering. So hitting buildings, tree trunks, and light poles, for example. And both of those co-polarizations are pretty good at that and do scatter more than the cross polarization. Whereas cross polarization returns the most with a volume scattering. So that's when we're dealing with really complex, multifaceted interactions in which there is depolarization. And that's what's causing a cross polarization signal to return. So as it's hitting a complex environment, maybe like imagine 3D Planko, and all of that signal is getting scattered in different directions and changed and whatnot, that will be able to cause that depolarization and will return a cross-polarized signal. In general, cross-polarized returns are smaller than co-polarized returns. So for example, a field that's pretty smooth, the VV return would still be pretty low, but VH would be very low. So you get that little bit of difference between those signals. So for example, here is a place in Germany, a region in Germany, with some forested land, agricultural land, and we can see the difference between a VV radar signal and HV polarization. So on the left here, there is VV, and on the right, there's HV. So what's interesting here is in the VV example, you can't quite differentiate the difference between a forested area. So I know from other information I have that here on the upper right quadrant, that's more of a forested area. But as you go towards these left hand side, that becomes more of a cropland. There's complex canopy structure. We know that from the HV returns, because we start to see a lot more variation across this northern, or the uppermost part of the radar image. We can see clearly delineated structures, and we can see that there's areas in which the returns are very different in HV, but they look way more similar in VV. So VV is telling us more about that surface roughness, and that the similar amount of vertically polarized returns means that it's understanding, or we're looking at that surface structure. But VH is telling us more about the volume and the amount of complex interactions that are occurring. So something else I'd like to note in this example is that there's a river on the bottom half of the image, and we can see in both VV and HV, they're really dark returns. Water, again, has that specular reflection, so it's not returning much in either the VV, and it doesn't also depolarize the signal, so there won't be a polarized signal either. Another way that we can visualize the differences between these polarizations is by performing a decomposition. Here's an example from UAV-SAR, in which the HH polarization is assigned a red colorization, HV is green, and VV is blue. And then by overlaying all of the different colors, we can get an idea of how the different returns are occurring across the image. So we at ASF have our own decomposition in which we do take 2 channels or 2 bands and then use that for building our colorization. So here's an example of a band scene, sorry. On the left-hand side is VV, in the middle is VH, and on the right-hand side is RGB, so that red, green, blue decomposition. And this is near southwest of New Delhi over Alwar, Canada, or India, oops. So I have the reference if you are interested into how we do these decompositions at ASF. But for the time being, for what's important here, the red band is to understand the VV returns. So there's some volume scattering. The green band explains or shows us more about the VH returns, where there's volume scattering. And the blue band is where there's surface scattering with very low volume scattering. And note in this image, there's very little, if not any blue. So there's not really any water or like exposed surfaces here, but we'll talk about that a little bit later. So as I'm looking at this image, I wanted to point out a couple different areas that caught my eye. Namely, I see on the right or the left-hand side, circled in red, that there is high or moderate VV returns and relatively high VH returns, and that's what we're seeing in the RGB decomposition as a really green area. So yeah, you can see here, there's a lot of green coming back. Something else I thought was really interesting was in the blue area here on the bottom right, and you can see in VV and VH, there's some signal or like maybe difference from the surrounding area, but it comes off really clear in the RGB that there's a box, like a big square that's way greener than the surrounding area. And I thought that was really interesting. So I wanted to explore that more to understand why that signal was there. And then finally, I noticed that there's a lot of return in the pink right here in VV, but very little in VH. And that shows up as very orange in the RGB composition. So I wanted to just get an idea of what was going on here. And so I zoomed in to get a ground truth. And so here on the left-hand side, I have an optical image from Google. You can see that this red area surrounding all this green around the city is like a cropland. So not super vegetated. And that's why we're seeing that red colorization in the decomposition. This red portion here is actually a nature preserve. It's like a tiger sanctuary, and it's really green and lush, and that's why we're getting that high volume scattering, a lot of volume scattering happening in those VH returns. There's this blue box here with that green box, and it's actually a military base. So we can see that the surrounding area is relatively low vegetation, and there's an actual wall with a gate. And then within that gate, there's vegetation, probably they're like watering everything. And so it's coming back with more volume scattering because there's a clear boundary just dictated by that wall. And that's why it shows up as a higher VH return. And then in pink area, I thought this was interesting because when there's a yellow color, that's when we would be seeing a lot of volume scattering and copolarized returns. But as you can see in this image here, there's lots of ability to have dihedral reflection, but there's some trees, but not necessarily a lot of complex structure. So it makes sense that that VH return would be lower for that type of area than maybe an area with more vegetation included on the streets and whatnot. So getting an idea of what's going on the ground helps us understand some of these patterns that we see in the VV, VH, and RGB decompositions. With Sentinel-1 data, RGB compositions are included when you submit your product. So if you can check, you can include them. So if you're ever interested, they're really gorgeous and beautiful to look at. So talking about water and what flat surfaces look like, here's an example near Cairo, Egypt, so right east of Cairo, Egypt. And we can see on the left-hand side in this slide, there is a Google screenshot again. And we can see there is a city and a body of water and then a lot of desert. And what that actually looks like in the RGB decomposition is lots of blue where we would expect for water, but this desert also shows up as blue because there's nothing to reflect back towards the sensor. So we're not getting very much for VV or VH returns. Flat water and flat desert, it's really hard to tell the difference when you're looking at a picture like this. So checking out what's going on is always really interesting, because when I first looked at this RGB, I thought it was just a port or something, but no, it's a desert. So really cool how that all works. Okay, so we can also leverage polarizations and bands that can provide the most insight into whatever application we're looking for. So since we know HV is a good measurement of how much vegetation there would be, it could be useful when understanding changes in vegetation before and after a wildfire. So this is what we're showing here in this slide, in which there is VH returns, or HV, sorry, HV returns from pre-fire and post-fire in Los Angeles, California. So on the left hand is a pre-fire HV image, and then on the right-hand side is post-fire. And what we can see is that they've gone and mapped the extent of the fire in black. So this black line throughout the image is where that fire ground truth, like they have mapped it out. And we can see that in the pre-fire image, the patterns of returns are pretty, they cross that boundary. There's not anything clearly differentiated between where that boundary had been mapped and outside of it. But on the right-hand side, the HV returns are quite a bit lower within that boundary. So what we are looking at here is a decrease in vegetation within that place where the wildfire has spread. And we even have some images to look at to compare what that would look like in the real world. So here we have a nice vegetated mountainous region, and that's likely that will cause more volumetric scattering and have higher HV returns. But on the right-hand side in the red, the fire's gone through and there's just less vegetation. So those HV returns, that volumetric scattering is going to be decreased compared to what it had been before. Likewise, we can leverage HH polarizations to understand flood extents. There's a couple different ways to map flood extents, but in this application, we use the concepts around reflection and scattering to understand how much flooding there's been. So as we know, open water bodies are going to return very little backscatter. And that's an example here. You can see there's a river, there is just water, and that's very dark in this image on the left. And then in the yellow, we can see there's a low vegetation area, and you can kind of see it, but pretty low returns there as well. And then there's some forested areas in which some return is happening, but it's pretty moderate, and we can see that right here in the blue. And then finally, since there's a flooded area, the combination of the signal hitting a flat surface and then bouncing off the tree, so it hits that flooded water, and all of the signals reflected away from the sensor, and then it hits a tree, and so it's reflected all back towards the sensor. So they're going to have really high backscatter returns in those flooded areas. And that will turn out as really bright in the image. So here in red, this red box, those are flooded trees. So we get an idea of the extent of the flooding in that forested region just by looking at that increase of backscatter. in the HH polarization. So polarization is one part of the story, but there's also the wavelength of the SAR signal that we can use to understand different things differently. So SAR band wavelengths range from 2.4 to 100 centimeters of length. This helps me understand the scale at which these SAR signals are propagating and what they might be interacting with. So on the right-hand side is going to be the smallest wavelength, and the X band, for example, will be traveling within really small wavelengths and will be interacting with objects much higher up. So it'll be interacting with objects sooner than a longer wavelength because it's just traveling at such a small scale. So in the schematic above the wavelength scale, we can see the X band might be interacting with the top surface of a canopy because that's what it's interacting with first, and that will be what it will be reflecting off of and returning. However, with longer wavelengths, such as the P wavelength, the wavelength will interact with objects further along, deeper down, and reflect back that structure. So with each band, there's different applications that can take advantage of the wavelength at which it's propagating and what it's actually sensitive to. When working with the different SAR bands, we have a couple different wavelengths to choose from. So there's the Ka, K, and Ku bands, but they're very rarely used for SAR and really specialized. So I'm just not going to talk about them much more. Then there is the smallest wavelength, the X band. So that's ranging from 2.4 to 3.8 centimeters, and that's going to be used in resolution SAR. So that might be little penetration into vegetation or an urban setting. The C band ranges from 3.8 centimeters and 7.5 centimeters. And that's kind of the SAR workhorse. So for example, Sentinel-1 is a C band sensor, and it is 5.54 centimeters. So this is useful for global mapping, detecting changes, and monitoring areas with low to moderate penetration. The S band ranges from 7.5 centimeters to 15 centimeters. It's used a little bit, but it's increasingly going to be used for SAR-based Earth observation, namely for agricultural monitoring, because it can be really sensitive to a light vegetation. And this will be used more and more. The L band is a medium resolution SAR, which might or does not provide as high resolution images as shorter SARs, but its ability to penetrate vegetation can be really advantageous. So the L band could be good for flood mapping because it can get through that vegetation and understand what's deeper down, like in a forested area, for example. Or it could be really helpful for characterizing canopy structure, especially in denser forests. And then finally, there's the P band, and that is the longest wavelength, ranging from 30 to 100 centimeters. It's relatively experimental, but could be useful for vegetation mapping and biomass estimation. So once again, if you recall back to the beginning of this presentation, we talked about a forested area in Germany, and we were looking at the different VV and HV polarizations across the forested and agricultural area. And this is the same region, but now we're looking at C-band and L-band data. On the left-hand side, I have schematics of what the C-band and L-band would look like, just approximately. In the middle, there's a C-band image in VV, and on the right-hand side, there's an L-band image in VV. And we can see there's some differences between these images. Namely, the C-band is returning very similar returns of VV across the different cropland and forested areas, as we mentioned before, but we're starting to see a lot more differentiation between those different areas in the L band. VV is not penetrating as deep into that vegetation, so it's providing that surface level information, whereas L band is able to get through that top canopy and tell us more about what's going underneath. One example of an interesting feature I saw was there's a faint linear feature here in the C band in C, but it's much more clear here in the L band. So this could be a road, and the canopy is covering it in this C band, so it's not able to be sensitive to that feature. But in the L band, the wavelengths are able to penetrate through that top canopy and tell us more about what's going on. Now, if we really want to get crazy, we can combine the differences in C band, L band, VV, and HV, and things get complicated. So not only are we looking at volumetric scattering differences and surface scattering, but we're possibly, we are looking at the difference between surface scattering. So we're starting to combine what we know about the fields, starting to combine what's interesting about soil moistures across fields in different environments that this whole area is experiencing. And in this case, L band and C band data, well, not in this case, L band and C band data are complementary, which is wonderful because NISAR will be L band data in Sentinel-1, which ASF we work with provide C band data. So we can start telling more complicated stories by combining them. But they do tell different stories. So keeping in mind that the L band image and a C band image are really hard to compare because they are telling us very different things about what we're looking at. So on that note, NISAR will be carrying 2 bands. The L band data is going to be a 24 centimeters wavelength, and dual pole observations are going to be available for nearly every cycle. So the L band will be observing nearly all the land, nearly all the time. The S band data, which will have a wavelength, or the signal will have a wavelength of 9 centimeters, is more specialized and will only be available for certain regions. So it'll be available for India and a couple other areas, but it's not really going to be globally available. Over land, NISAR will be primarily HH and HV polarizations, but there's opportunities for quad pole polarizations in certain regions. So we can use everything that we've discussed to understand NISAR's strategy in targeting its mission goals. So in this map, we're describing different solid Earth targets. So as we can see with the different colorizations, some targets would be landslides, aquifers, permafrost, surface deformation from geophysical changes, and there's some specific volcanoes and oil and gas fields that that we're looking to target. And understanding these targets help guide observation strategies, so we can use appropriate bands and polarizations for appropriate applications. So here is an observation plan shared during a presentation by the NISAR team last year. And we can see the different availability of SAR poles and wavelengths as a global image. So India, for example, you can see has LSAR and SAR available, will have it available for it. Then there's Antarctica, this specialized sea ice quadrant, and Greenland that also will have LSAR and SAR capabilities or data available. Background land will have dual pole for the majority of it, but there's some areas in Africa and South America with a single pole only. In North America, there is primarily dual pole availability, but there's some regions in which the quad pole will be available. So here in Alaska, there's a little bit to look at permafrost. And then the Great Lakes region also will be having some quad pole data available. All right, and with that, I'm going to leave some extra resources if you're interested in learning more. We have the documentation for RGB decomposition that we do here at ASF. And then I'm also including links to the NISAR team's wildfire and flooding ArcGIS story maps. So those HV and HH examples that I discussed, you can learn more about them there. Really gorgeous, and I highly recommend checking them out. All right. Thank you. Heidi can take it away. Tell us more about other applications.
All right, thanks, Jackie. Yeah, so at this point, we'll be pivoting and taking some of the things that we've learned and actually applying them to actual data sets and getting into the weeds and exploring some ways that we can use the RTC products to actually tell us information. You can go to the next slide, Jackie. So we'll be doing two different applications. One will be delineating surface water, and then the other is using log differencing to detect change on the landscape. For surface water mapping, we take advantage of what we've been talking about over and over, that calm surface water tends to have very low backscatter. And this can help differentiate it from the surrounding area. And if you go back to the previous slide, Jackie, so we have the specular reflection that's occurring over the water, and then compared to the diffuse scattering that occurs on the land nearby, it gives a really nice contrast between the water surface and the land that's surrounding that water. So the next slide. On a calm day, we see that surface water has very low backscatter. But that really changes for the VV polarization when there are windy conditions. So in this slide, this imagery is from the North Slope of Alaska, where there are lots and lots of lakes all over the landscape, and very little terrain and very little vegetation. Any vegetation that's there is very short. It does not grow very tall. So on a calm day, if we look at the images on the top, both the VV and the VH return very low backscatter for the water surface. On a windy day, however, which you can see at the bottom, the VV, if you were to just look at this image and not know that there were lakes on the landscape, you might not even realize that you're looking at hundreds of lakes dotted amidst the tundra. The surface roughness and of the water and of the surrounding tundra are so similar that the backscatter is quite similar from the water and the vegetation. So it makes it much more difficult to delineate the water from the land. If we look at the VH, if you look at the VH in the bottom right corner, however, on that windy day, there is still very little impact on the VH signal. And that's because even on a windy day, the waves are not so high that you're creating a volume. So it's still just a surface. It's a very rough surface. And so there are more angles available for sending that signal back to the sensor. But anything that is coming back is generally still vertically polarized. So there's not that mechanism for depolarizing the incoming signal. So any of the signal that is coming back from those rough waves, it is still vertically polarized. In many cases, it is more robust to use the VV to delineate water, just because the amounts of backscatter are generally overall higher for the VV polarization than for VH. But in cases where you do have situations like this, where the landscape is prone to wind conditions, it may be more valuable to use the VH for some situations. So it's something to keep in mind if you're trying to delineate water and the conditions are windy. You may need to consider using the VH rather than the VV. All right, next slide. The second application that we'll be looking at is the log difference for change detection. A very quick and easy way to identify if there are differences between two RTC acquisitions is to simply take the log difference, or take the log ratio of those two RTC images. And then the areas that have high differences from one to the other will show up very clearly. And we can set a color symbology even to help us visualize that and even quantify the amount of change. So that will be the second exercise that I'll go through. And next slide. This whole workflow that I'll be demonstrating is actually all documented in a series of tutorials, and it's available at the bottom of the RTC On Demand tutorial. So if you've taken a look at that, if you scroll down to the bottom, you can see that there's a list of each one of these tutorials that it walks you through step by step. So if you want to work through these same workflows on your own, that is available as a resource. And I see we have a question that's just come up. The recording of today, it will probably take a few weeks for Alex to do the editing of these recordings, but they will be available on ASF's YouTube channel, which is linked in the presentation. So, yeah. Okay, so if you do want to work through this on your own and not with the video, the tutorials really do walk you through step by step on exactly what I'm doing in this particular demonstration. I will be doing the demonstration using ArcGIS Pro. You can use any other GIS software. If you are using ArcGIS, we do have a custom toolbox that's available, and I'll be demonstrating today using tools from our toolbox, and that's available for download from our website, and it works either in ArcMap or ArcGIS Pro. If you are working in QGIS and you want to do these same workflows, most of even though we have these custom tools, the actual raster functions behind that, the tools are quite straightforward. And so if you do want to see the workflow that you would use in QGIS, get in touch with me and I can send you a presentation that walks through the same commands that you would use in a QGIS environment. All right, and with that, I think I'll share my screen. And we'll get into the data. I see that there are a couple of questions. Are there things that need to be addressed before I move on, or should we take a look at those? So there's a question about specific reason for quad pole coverage in a selected area. So yesterday I talked about the trade-offs that need to be considered when you are when you're acquiring data. Quad pole data is really handy. It tells you a lot of information, but there is a cost of acquiring it. And so usually there's a smaller footprint, so you get less coverage from any acquisition that is in quad pole, and it's an expensive data set to produce. So generally when there's a mission plan that's being drawn up, if there are places that the mission planning group is particularly interested in having quad pole data for, that may be prioritized. It may be the country who's flying the instrument may prioritize areas that are of interest to their nation, or if there are areas of global interest for whatever reason. So it tends to be a kind of a patchwork of areas where there might be quad pole data available. When quad pole data is more common for airborne missions. So for example, UAV SAR may often have quad pole data available. And but that's an airborne mission. There are different considerations when dealing with the data. It's already a fairly narrow targeted area, and so there's less of a trade-off. You're flying a very specific mission over a specific area for a specific purpose, so it's more likely to have the quad pole data. But most of the large imaging missions, predominantly, so Sentinel-1, for example, is just a dual pole sensor. It doesn't have the capabilities of quad pole collection. All right, so let's dig into the data. I have ordered some imagery from Vertex using the on-demand processing. And when you do download those data sets, when they're complete, they're in zip files. I've extracted those zip files to my computer, and now we can take a look at what's inside of the RTC folder. There are some options when you're ordering imagery in Vertex. You can choose to include some additional layers. And in this case, I have not included a lot of those. So, and yet there are still quite a few files that are in that folder along with the RTC images. If you're new to the RTC products, I really encourage you to look at the README, which is included with all of the products. It goes through each one of the files that's included with the product package. It gives you a lot of information and background and links and resources. So when you're first starting out with any of our on-demand products, definitely take a look at the README file, which will walk you through what you would expect to see in this folder. So the products that I'm actually interested in using are the RTC products, and those are a .tiff extension, and there's one for each polarization. So you can see here, just a quick question, can everyone see my mouse okay?
Yes.
Yeah, we can see it pretty well.
Okay, okay. So here we have a VV geotiff and a VH geotiff. So I'm going to bring the VV into my project, and it shows up here on the mitten of Michigan in the United States. So I have an RTC from the 15th of May, 2020. And then I'm also going to add an RTC in VV polarization from the 27th of May, that same year. Now you can see clearly things have changed. Something's going on here. And that something was a significant rain event that caused extensive flooding across the state. We're going to zoom in to the Shiawassee National Wildlife Refuge. And this is an area that even before the rainfall, it's quite a lot of wetlands. It's a wetland complex. There's a river that runs into it, lots of birds and ducks, and it's generally a fairly wet environment. But after the rains, you can see that there was much more surface water. So all of these dark areas are those agricultural fields nearby that ended up flooding as a result of that rainfall. Alex mentioned when talking about Vertex that when you're choosing to submit RTC jobs, you have a choice of scales that you can use for the output product. And I have chosen amplitude as the scale for my output products. The kind of the standard SAR scale is power, but when you bring a power image into a GIS, often it looks very dark. There's not a lot of definition of the features. And that's because many of the values are very close to zero. But if you have a few bright scatterers, they can really skew the dynamic range. So you can have like 99.99% of your pixels are less than 1. And then you have 1 pixel or 2 pixels if there's a corner reflector or a sharp building somewhere that can have, you know, values of 100. And so that really skews the way that the imagery is displayed because everything looks dark. The amplitude is simply the square root of the power values. And so it kind of condenses the dynamic range of the image a little bit. So those very small values that are close to 0, decimal points that are close to 0, all of those become larger, and then any of those very large values become smaller. So you've kind of shrunk that dynamic range. So in general, amplitude images look fairly reasonable if you just want to examine the features. They visualize quite nicely. So power is fine for statistical analysis, for example. But if you're actually interested in looking at the image, I often find that the amplitude images are the most easy to look at and to identify features. There is a third scale, which is dB. And dB is 10 times the log 10 of the power values. And the dB really stretches out the very low end, all of those numbers that have lots of decimal points. So you get a lot more definition in the very dark pixels, but then the terrain or the lighter pixels tend to be quite washed out. But dB is very good if you're trying to delineate water on the surface water from the surrounding terrain, because the dark pixels are quite different than from the uplands. So I'm going to take this amplitude image and convert it into a dB scale image. I have downloaded the ArcGIS toolbox. I mentioned that ASF has a custom toolbox, and you can just go to our website and download it. It's a zip file. You extract this toolbox anywhere on your computer, and you can use it just like any other ArcGIS toolbox. So I'll open this tool for scale conversion. And I'll select my image from my RTC folder. I'll select the one from the 27th after the flooding and select the VV-TIFF. Now you can see that the tool recognizes that this is an amplitude image, and that's because of the naming convention of the HYPE generated on-demand RTC products. So this second letter right here tells me that this is an amplitude image. That would be either A, P, or D, depending on the type of the scale. So if I've changed the name of my input TIFF, I would have to actually go in and manually select which one of these options it was. But because I have I haven't changed the file name, it knows that it's an amplitude image. I'll select dB, which is what I want to change it to. And then I can choose a destination folder. By default, it just uses the same folder for the as where the source raster is. But I want to choose a different place. So I'll save it here in my output products. By default, for the output raster, the name is just the input file plus an underscore dB. And I'll keep that default and run the tool. And you can see right away, there's a huge visual difference. So all of those dark pixels become very clear on the landscape, and everything else kind of washes out. I'm going to go to the symbology tab for this layer. So I'll just select that layer, and you can right-click the layer and select symbology if you want to get to it that way. And I'm going to change it from a stretch symbology to a classified symbology. I want to see just what I think is water versus what's not water. So I'll classify it, and I'll set the number of classes to 2, just water and not water. I'll change my colors so that the low values will be blue, and then the other values will be transparent. Okay, so ArcGIS has just done found a natural break and assigned a value for that threshold, but I want to pick my own threshold that I think really delineates the water from everything else. So I can go to this histogram tab, and here you can see a histogram of all the pixels in the image. Now, when we do have an image that has a lot of surface water, we tend to see a bimodal distribution of the pixel values, where you have this one peak that is all those very dark values, which in this case are surface water. Then you have another peak that is everything else. A great way to start when you're trying to pick a threshold for what's water versus not water is to look for the difference, the change or that valley between those two peaks. So I'm just going to drag the threshold to be at the bottom of that valley. And at this point now, I can see that approximates those really dark pixels quite well. So I'll go back to my classes tab, and I'm just going to set this to a nice round number. So I'll pick -18 as my threshold. Now, it's important to note that there is no hard and fast rule for delineating surface water. There's not a dB value that just works everywhere. It's a little bit tricky, and it depends on your particular scenario, which your site, what the water conditions are, how it relates to the surroundings, the wind conditions. So there, you have to go in and take a look and figure out which threshold actually works for your particular situation. So when we have efforts to create a global water map, for example, that makes it a little bit tricky. But if you're looking at a very specific area, then you can just use what you know about that site to choose an appropriate value. All right, so I now have this nice visualization, but it's still just my dB raster. If I click on a pixel here, it still tells me the entire the dB value. And that may be fine. Maybe this is all that you need, but in some cases you may actually want a classified raster, a mask, as it were, that you can use for analysis or for overlays with other maps. So we can take this raster that's just all in dB and convert it into a classified raster by using the reclassify RTC tool that's in the ASF toolbox. There are also reclassification tools elsewhere. This just makes it really easy for this particular scenario, but you can use your regular method to reclassify your RTC if you already have that workflow. So I'll select my dB raster here, refresh. Okay, so here's my dB raster, and I'll save it to my output products. And then by default, it takes the name of the input file and then adds a _reclass tag. And I like to add a designation of what value I actually used for my threshold. You may want to try a few different values and then compare it to other data and see which threshold gives you the best results. So here I have a -18 dB, so I'll enter that as my threshold and run the tool. And now I have an output in my map that if I click on one of the pixels with water, you can see it now. It has a value of 1 rather than the full dB value. If I click on an area that doesn't have water, it just has a no data value. So I can use this mask to run zonal statistics or to calculate area that's covered by pixels with a value of 1, or any other comparison to another raster. I can use it to multiply. You've got this mask now that can be used for raster analysis. Let's move to a different part of the state. I'll turn this off for a moment. Up to Edenville. So if I compare the before image to the water mass that we've just created after the flooding event, you can see that something happened here. So what happened is that there was a dam breach. So there's a dam right here that was damaged due to the high rainfall, and the reservoir drained out. And in fact, it then caused a failure in the next dam, which also drained out. So we lost a lot of surface water from the landscape. Now that's very clear if I'm looking right at this site, but if I'm zoomed out to the whole image and I just kind of compare, there's so much going on that little spot there where the dam failures occurred isn't very obvious in my image. So one way to quickly identify areas that have undergone change is to do a log difference. So we have this calculate log difference tool in our toolbox. And I'll choose the most recent SAR acquisition. So we'll go to So the most recent is from the 27th of May. And I'll choose my VV image. Now notice I've gone back to using my amplitude images. And this is because dB is already in a log scale. So you'd be taking the log of a log, which is not optimal. So it's best to use either the amplitude, or power also works, but amplitude gives quite nice results. So I'll choose my VV image from the 27th, and then I'll choose my reference raster, which is from before the flooding. So from the 15th, here's the VV. And again, I'll choose my output folder to be for my output products. And then the file name is just, it combines the two input files and then adds an underscore log diff to the end. So this makes for a very, very long file name. So you may want to change that, but for now, I'll just run it with the defaults. Okay, at this point, it is a grayscale image, but even so, even with a grayscale, that feature suddenly becomes very obvious. But I'm going to help my eyes even more and go back to my symbology tab and set a classification again. So I'll choose a color scheme that has a really different color on each end. So here, this one goes from blue to red. And even there, that helps kind of pick out some of the features, but I want to really use the values to quantify where is undergoing the most change. So I'll set these to be minus 0.5, and this will vary depending on what's going on in your image. But generally, you can consider for amplitude, if values are between minus 0.1 and 0.1, usually we consider that to be not changed. Like that's pretty stable. Anything else, depending on the sensitivity of your changes, there may be some changes that have a huge value, and so you can set your thresholds to be even higher if the only thing you're interested in seeing are the very, very largest amounts of change. But I'll use 0.5 for the lower end, minus 0.1. So this minus 0.1 to 0.1 is that area that I'm considering to be essentially no change. And then I'll change this to 0.3 positive. So here I'm going to set this color to be even more neutral. So this category is from minus 0.1 to 0.1 is considered no change. So you can see that there was a lot of change that happened throughout the state, and that's shown by this green. That's moderate amount of change. It's not nothing, but and it's widespread. But then the areas that really underwent a very sharp change, those become much more obvious. Here we have that reservoir that was breached, and we have a positive change. So as long as you're using the tool so that it's using the reference raster as the previous prior to the event, and then the second raster as the comparison raster, the direction will indicate the direction of the change. So, the sign will indicate the direction of the change. So if I have a positive value, that means that the backscatter has increased from the first image to the second image. So here, it used to be that these reservoirs were filled with water, so they had very low backscatter in the original image. But then once the dam was breached, all that water drained out, and now you have the soil underneath, which has a much greater texture and is able to reflect the signal more back towards the sensor. So you've increased the backscatter potential of that area by removing that surface water. So that shows up clearly as a high increase in backscatter. If we look down at that Shiawassee National Wildlife Refuge area, you can see that a lot of it was the same. It didn't change. It was already wet. There was already surface water before and after. But then those fields that were beyond the wetlands that did have standing water afterwards, those decreased in their backscatter. And that's because they were croplands. They were reflecting backscatter due to the texture of the field. There may have even been some vegetation to help out with that. And then that was replaced by standing water. So once you have standing water on top of all that, you have the specular reflection that results in very low backscatter. So we have a significant decrease in backscatter in those areas. Now, that illustrates the two things that I was looking at specifically. But if I zoom out, I can see that there are other places that I didn't even look at before. It's like I can then zoom in and say, oh, what's happening here? And it turns out that these are some lakes that had their ephemeral ponds that were dry beforehand. They had nicely saturated soils, but they didn't have any standing water. And then or they did have standing water, and then afterwards it was lost. So you have that increase in backscatter. You have, sorry, these ephemeral ponds, they were dry and then they filled up. And by the time we took the second image, it was just saturated soil, which is very, very bright. And so you have that increase in backscatter from the dry soil that had not yet collected any water to having that saturated soil after the pond had filled and then drained. So these log difference files can just really bring your eye to areas where change has taken place. And also areas where change has taken place that you might not care about. So here we have the lake. This is Lake Huron, which is very large, and it's very susceptible to wind conditions. When you have it's like the ocean, essentially. When you have such a large extent of open water, on days where there is wind that wouldn't really impact smaller lakes, especially if they're protected by vegetation, you can get a lot of activity on the lake. So it turns out that in the image after the flooding, the conditions were actually very calm. And so you have very low backscatter throughout on the lake. Whereas before the flooding, that acquisition was actually very windy. It was a very windy day. And you can actually see the wave patterns on the surface of the water. And so when you run that log difference, you can see there's this area here that was fairly dark in both, and that one actually increased in backscatter, whereas almost everything else decreased in backscatter because it was so much calmer, the second acquisition. But that's just looking at wind conditions. This isn't a permanent or a significant change on the landscape. So it's important to be aware of what's in your image and what change you're actually interested in. So that's the log differencing. And I do want to go back to the water delineation just for a moment and mention, so this use case here is quite good because I have water that's surrounded by something that's really has a very different backscatter characteristic. If we were doing this same analysis in that image that Jackie showed in Egypt, where you have the Suez Canal, which looks very blue, it's the lake is very blue, but then right next to it, you have sand dunes. You wouldn't be able to use the same type of thresholding in that situation. So it's very important to be aware of the image that you're working with and the limitations. So this surface water mapping approach works really well in situations like this one, where you have croplands that are being flooded. It does not work as well if the flooding is in an arid region. And that wraps up the demo. Are there any questions? Oh, it looks like we've got some things going on in chat. Are there any questions to address?
I think we've done a fair job of handling most of them, but
Okay.
I'm sure people might have new questions.
Right. Well, we'll take a few moments, or you can think about it too, and I'll pass it over to Alex. And if anyone still needs help getting their environment set up for the Open Science Lab, we'll be taking a break after this, and this is a great time to work through any of those issues that you might be having.
Thanks, Heidi. Yeah, so if anybody does not yet have a Open Science Lab account, or if you signed up for one but still need your account authorized, would you please send me a private message in the chat, including your OpenStar Lab username or at least the email address that you used to sign up for your account with.
Okay, and I've got a few questions too from the Q&A. So how to identify water in a wooded area? This can be tricky. So if you have an L-band sensor, it really depends on the density of the vegetation. So even with C-band sensor, it may be able to penetrate moderate vegetation. So as Jackie mentioned, you might see actually much brighter returns underneath vegetation. So you might actually be able to delineate based on the brightness if you're looking at flooded vegetation. But in many cases, the C-band is not long enough wavelength to penetrate through. So for looking at inundated vegetation, often L-band is a more suitable sensor. So if you have L-band data, it's much easier to map that inundated vegetation. But in some cases, it may also work with C-band. So you'd be doing kind of an opposite threshold where you'd be looking for the brightest area. But it's really situation dependent. It would depend on whether you have an appropriate sensor for being able to see through the vegetation. And then if the signal is clear enough and if you're able to delineate it from the inundated vegetation. But with L-band, it's often very, very successful to be able to look at inundated vegetation. So the VV and not the VH. So yes, this is a choice that's made. So for simplicity, if you're just doing a quick and easy analysis, using a single polarization makes it very easy. There are a number of ways that you can combine. This was the simplest approach for doing a water threshold. There are a lot of different approaches, and you can get quite complex actually in the way that you combine VV and VH. So you can get in touch with us if you want some references to specific papers that are more focused on a more robust workflow for combining the two polarizations, or you can experiment yourself with your particular area to see if combining in the VV and the VH in some way or another would actually give you more robust results. So this was just a demonstration of a quick and easy way to do it if your site supports that quick and easy method. If you want to do something more complex, there are lots of options out there, but you'd have to determine which works best for your particular area. Was there any follow-up for that?
I think someone asked about the threshold. Can we fix the threshold at nearby to NESC in generic case?
Sorry, I couldn't hear the end of the question.
It's in the chat. Can you
okay.
fix the threshold at nearby to NESC in generic cases?
NES. I don't know what NESZ stands for.
Noise equivalent.
Oh, a noise equivalent sigma naught. I mean, you can fix the threshold at anything that you want. So I just did it visually, but you can use, so sometimes people will do a Gaussian analysis to determine where exactly between those two peaks you would, the peaks actually is where the actual valley is, or the low point. I just did it visually. It really depends on what kind of analysis you're doing and how robust you want to be. If you're just looking for a way to quickly pass on to other people, this is the surface area that's covered by the water as I can see it. You can just do that visual assignation, but if you want to use other thresholds, you can set it to anything and check and see how well it performs. The open SAR Lab split window method for flood mapping. Yeah, so there are, and maybe I'll have Jackie speak to this more, but there are algorithms that are in development for looking at surface water detections, and it uses a much more complex workflow than just setting a simple threshold for one of the polarizations. So there are, I'm not sure if that's available in OpenSAR Lab. Alex or Jackie, do you have anything to add?
I'm sorry, I was just typing an answer to a question and I didn't quite hear. Could you?
So for the surface water mapping, is that workflow available in
The HydroSAR notebooks are available in OpenSAR Lab.
Okay.
Yeah.
Okay. Yeah. So if you want a more complex way to interact with surface water analysis, that is an option to try.
We also have a Python module that is called ASF tools, and that also has flood mapping and flood depth options. I can link it in the chat, but going through the notebook in OSL would probably be a lot easier to get started with.
Okay, if there are no other questions for now, I think we can head to the break. Do we want to stay on target for returning at the top of the hour, or let's see.
Yeah, that sounds good. And I know that one participant has had trouble building the environment, so maybe I'll take this opportunity to just share my, well, I have to start OpenSAR Lab up because I haven't done it yet, but then I'll share my screen and just walk through building that environment one more time over the break. So, but don't feel that you have to stick around to watch that unless you're having trouble building your environment.
Okay, that sounds good. So for those who need to build the environment, feel free to stick around. Otherwise, we'll start again with Forrest's presentation at the top of the hour. So 7 a.m. here, and whatever hour it is, wherever you might be.
And so when you arrive in OpenSAR Lab, you should see a launcher window such as this, unless you've previously done work in your account, in which case you may see another notebook or something. And so in the home directory here, so assuming you've already cloned in the tutorials repo, the environment that we'll want to build is located in that tutorials repo in the IGARS 2023 directory, in the environment.yaml here. And so if we open that up, you can see that this will create an ASF IGARS 2023 tutorial conda environment, including these packages. And so I'm just going to click on the left folder icon at the up here to get back to my home directory. And in order to build this environment, I'm going to use a notebook in the conda environments directory. So I'll open up the conda environments directory and then open that create OSL conda environments notebook. And I'm just going to clear my output here, restart the kernel. And then once you're in this notebook, you can run the first several code cells. And then in the fourth code cell here, it offers you an option to build a an environment from one of the YAMLs that we've provided here in this environment configs directory as part of this content environments repository, or you can direct the notebook to a YAML in a different location. And so that's what we want to do in this case is point the notebook to a YAML in the tutorials repo that we've cloned. So I'm going to select use another YAML and then continue running the notebook. And now there's an option to select that YAML in the file chooser. So I'll open this up and I have to back out to the previous directory. So I'll click on the folder icon here with the two periods. And that will allow me to back out. And then I'll go into the tutorials directory, and then into the IGARS 2023 directory. And then I'll select the environment.yaml file and click the select button. And once this pops up with file path here in orange, you know that you're ready to move on to the next code cell. And so you have to click into the next code cell. If you don't click into the next code cell, if you just were to select a particular path here and then click the play button again, it's just going to rerun the same code cell and once again make you reselect that that YAML. So oops. So once you've selected your YAML here, you have to click into the following code cell, and then you can continue running those. And then I will just run this, and this is going to overwrite my my previous copy of that environment. And of course, if you don't have one yet, then it will just create that environment. And so once this is finished building, we should have all of the packages that we need in order to run the heat maps, the Landslide heat maps notebook. And so this IGARS Landslide heat maps notebook is the notebook that we'll be using today. There is a second notebook that does an interferometric time series analysis of Mount Edgecumbe, which is a volcano in Alaska. However, this uses a different environment. So if you try to open up this and run this notebook, unless you have previously built the NISAR analysis environment, which is present in our pre-populated configs here, right here, the NISAR analysis environment, unless you've also built this environment, you won't be able to run that second notebook. But once again, we are not covering this notebook during the workshop today. So that's not necessary for this workshop. All you need to do for this workshop is to install this, the environment from this YAML here, and then we'll be running this Landslide notebook. And so this will take a few minutes to complete. And I'll just leave it on screen here so that you can see what the output of the code cell looks like when it's completed, creating that environment. Oh, and Dr. Rao, I just saw your message in chat about running the Geos 657 course material. And so yes, it's likely that you'll need to install a different environment for that one. So let's see if I head out here to the Geos 657 labs, and then I'll just open a random lab here. And if you look up, once this finishes opening, okay, yes. And so because in this account, I have not built any other additional content environments, when I opened this lab, it expected to find a particular kernel and couldn't find it. And so now it's asking me to select a different kernel. And so for the moment, I will select no kernel. Of course, now we can't see what the expected kernel is, but there should be, let's see. So if you look down in the initial, actually, to start with, I'm going to select the base kernel. Oops. Because there are some code cells in here that will direct me towards building the correct environment. So if you don't have the kernel and it gives you that pop-up, just select the base kernel and then run the first couple code cells, and you'll see this warning. This notebook should be run using the RTC analysis conda environment. However, it's currently using the base conda environment. And so using that same notebook that we use to create our other environment, we can head back over here and so it looks like the notebook that I was building, or the environment that I was building, has completed. And so this is the output that you would expect to see once an environment has successfully completed. But Dr. Rao, since you needed I think the RTC analysis, yes, RTC analysis conda environment for this particular notebook, if I wanted to build that, I would head back up towards the top of the notebook, and I would just select use an ASF environment YAML. And then I would get my list of ASF sort of pre-built, or not pre-built, but provided YAMLs. And so I'll just select the RTC analysis environment and then run the remaining code cells. And then that should build that RTC analysis environment. And so different notebooks in there probably require different environments. The two that you're probably going to need to run all of those notebooks are the RTC analysis and the NISAR analysis environments.
All right, we're a little bit past the top of the hour, so I think we're probably good to start up again. Just to introduce myself to you all. Hello, I'm Forrest Williams. I work at ASF along with the rest of the people who have been presenting to you over the past 2 days. My background is really in SAR and NISAR monitoring of landslide, so I'm really excited to share this tutorial that we built that goes through an example of how you can identify landslide scars with an RTC analysis. So to begin with, the first thing you'll have to do is log into OpenSAR Lab and then clone in the repository that has the tutorial that you'll be working through today. So in order to do that, when you're in your OpenSAR Lab instance, press this big plus button and click on terminal. And then type in this command, which is git clone, and then the URL to the tutorial repository we'll be using. I'm also putting that in chat if you want to grab that yourself. And just for reference, that URL in that git clone command is also where you can go to take a look at these tutorials if you ever want to look at them on your own time later on. So when we call this command, that will basically download the tutorial that we'll be using into our directory. And then over here in this file navigation window, we'll now have a tutorials directory. Inside of this directory, we'll double click on that, go into the IGARS 2023 tutorial directory, and then even further, go and select this IGARS landslide heat maps Python notebook. And then as soon as this pops up, you'll want to select the appropriate kernel for running your workbook. My name is a little bit different than you all's, but if you select the kernel that Alex helped you set up, you should be good to go. So here we are in the main part of the notebook. So just to give you a little background on what we're going to be doing today, we'll be analyzing a set of landslides that occurred after a magnitude 7.2 earthquake that occurred in Haiti in early 2021. This was a pretty devastating event. A lot of people were hurt and lost their lives. And one of the major impacts of this earthquake was a massive amount of landsliding that closed roads, damaged a lot of infrastructure. And directly after the earthquake hit in Haiti, they needed some way to tell where the damage was the most so that they could get help and emergency medical personnel into those areas as soon as possible. Unfortunately, because there also happened to be a major tropical storm occurring at the same time as this earthquake, basically there was cloud cover over the entire island for many weeks after the landslide. And this made it very difficult to use any optical imagery to determine where the landslides were. And for that reason, SAR really shined in this use case. Because it can see through clouds, it was one of the few types of imagery that we could use to identify where the landslides were occurring directly after the earthquake occurred. So it had an actual impact when this earthquake struck. This isn't just a toy example. And based on some of the work they did, they also published a scientific publication detailing how they actually did this landslide identification. And that paper is named Handwerker et al. 2022. If you'd like to go take a look at this paper and read about the method they use and the one we'll be using in this notebook, you can go ahead and click on that link, and it'll take you to the paper on this topic. And now what we'll actually be doing in this notebook is recreating the analysis they used in this paper to show you how you can use RTC data to actually identify landslide occurrences. So when we're talking about landslides, it's important to talk about the different types of landslides that exist and how they relate to SAR imagery analyses. So in general, you can group landslides into two broad categories. Landslides that fail very slowly and tend to move consistently across the landscape for a long period of time. We call these creeping landslides. And then you also have sets of landslides that fail catastrophically immediately. Basically, an event like an earthquake occurs, and almost immediately massive amounts of debris and rocks slide off of hill slopes, and we call those catastrophic or fast landslides. And in this case, for the Haiti earthquake, the landslides that we're studying are in this catastrophic category. And because they're catastrophic and fail, in matters of seconds, we can't use techniques like NISAR, which track motion over long periods of time, to actually identify where these landslides are. Instead of tracking landslide motion directly, we have to use a proxy for where these landslides are occurring. And to do this, we're using a simple heuristic, which is that before a landslide occurs, the area where the landslide is typically covered by some sort of vegetation. However, after the landslide occurs and the debris moves off of the landscape area, you're left behind with what we call a landslide scar. And this is an open area where there's no longer vegetation. Instead, there's just bare ground. And what we'll actually be detecting in this analysis is those scars. We'll be trying to basically see, where was there vegetation in a previous image, a previous SAR RTC, and there is now not that that vegetation or that signature vegetation in the second RTC image. So just as a little chance for you guys to participate, if we're trying to identify the loss of vegetation related to landslide occurrences, which polarization do you think we should use for our analysis? Should we use VV polarization, where we're vertically receiving or vertically sending and vertically receiving, or should we use a VH polarization, where we're sending vertically but receiving horizontally? It'd be interesting for you guys to try and type your guesses into the chat, and we can kind of see what you guys think. Okay, I see one vote for VV, another vote for VH. Okay, well, I hope you guys have had a little bit of time to think about it. The answer in this case is VH, because what we're trying to detect in particular is the loss of vegetation, and vegetation tends to exhibit volume scattering most often. So VH is going to be, VH is more sensitive to these types of volume scatterers, and so VH is what we're going to be using in this analysis. So moving on, the first things you want to do is just start running the first couple cells of this notebook. You can run cells on this notebook by simply navigating to it, and you'll know which cell you're next to by this little blue bar next to it. And then you can just simply press Shift Enter and it will run the cell for you. So moving on, the first thing we want to do is basically create a set of RTC images that we can use for analysis. Now, so that we can fit this whole tutorial within the time constraints we have, we have staged some of the data for you so that you don't have to request the processing of the RTCs yourself and then actually wait for them to process. But all the cells for doing that are in this notebook if you want to do it yourself later on. So the first thing that we'll do to try and define which images we want to create is create a window of time about one year around when this earthquake and the landslides occurred. So here in this cell, we define a start time, which was August in 2020, an end time in September 2021, and an event time, which is when the earthquake actually occurred in August 2021. So if we do that, run a search with those parameters over our study area using the ASF search Python utility, we can get results and take a look at where this search has returned data for. And in this case, the earthquake mainly occurred in this area of Haiti. And here, this black box represents the area that our SAR images cover. Here, we have a stack of 34 images between these in this year surrounding the event. And the coverage, SAR scenes tend to be large, so this easily covers the area where the landslide occurred, which is roughly this zone on the western part of Haiti. Excuse me. So now that we have a sense for where our scenes are in space, let's take a look at where our scenes are in time. So here we have a plot where we just have our image number on the y-axis and the date of that image on the x. And this red bar represents the time that the earthquake actually occurred. So one thing you'll notice is that, or in comparison to the water mapping tutorial that Heidi gave, is that we're not just using one image before a given time period, one image after it. Instead, we're using a larger series of images. And this is to try and reduce the amount of noise in the analysis. One thing that you've heard about in previous SAR lectures, most likely, is this phenomenon called speckle. And speckle basically introduces a certain randomness into the data that makes it hard to reliably detect changes in most scenarios. However, one technique that we can use to actually reduce the effect of speckle in these types of log differencing analyses is basically take temporal averages of our RTC imagery before and after a given time to basically create a synthesized pre-event image that reduces the effect of speckle and a synthesized post-event image that also has a reduced speckle. In this case, we're using a much longer series of images for the pre-event time series stack than for the post-time series stack. And that's because our nominal or normal condition isn't changing much over the year, so we can reliably stack a set of images over 1 year to try and further reduce speckle. But as you might have guessed, soon after a landslide occurs, vegetation will start to regrow. So we don't want to expand our post-event window too far because we want to make sure that those very fresh landslide scars are still visible in our imagery. So just to reiterate, what we're going to do from here is actually request the processing of these RTCs, stack them into an RTC time series, average out all of the images before the event to create a pre-event image or synthesized image, and then average the post-event images, and then combine those two images into a log differencing analysis similar to what we did for water detection. So the next couple cells that you'll see here in this section number 2 all have asterisks next to them. These are the cells for actually requesting the creation of the RTCs we're going to be using today. All of these cells are commented out for now because we have staged some of this data for you. But if you want to go back later on and process this data yourself, feel free to go ahead and uncomment these cells and run them. It's also a nice short tutorial of how you actually can request the processing of RTC data from ASF via our Python module. So we'll just run through those cells quickly. And then we'll move into section number 5, which will be the section where we actually download and extract the stage data. So first, we'll download the stage data from an Amazon Web Services S3 bucket where we stored it. And then once it's done downloading, we'll go ahead and unzip and extract all of the relevant files to this Haiti RTCs directory here. And this cell will take a few minutes to run. So if you guys have any questions about the overall method or about the Haiti example in particular, feel free to ask them now. I see a question about running the data locally instead of AWS Cloud. As long as you set up the Conda environment like Alex showed you on your own local machine, yes, these notebooks will run on your local machine as well. In general, though, we do recommend using our open SAR lab whenever possible, just because it is a very nice interface where we've kind of taken the time to create a really nice environment for you where running these types of analyses are relatively simple. There's a lot of behind the scenes work that Alex's team does to make sure that getting started with these types of SAR analyses, you can actually start working with the SAR analyses and don't have to worry about computer and installation issues right away. Okay, so our data is downloaded at this point, and now we're just waiting for it to be extracted. If you're at the top level of your Open SAR Lab file tree directory, under the tutorials folder, you'll see our IGARS 2023. And then here in IGARS 2023, here is the zipped file that we downloaded from the Amazon S3 bucket. And here is the Haiti RTCs folder that is being created as we extract the data. Inside of this folder, you can see a set of RTC images that have been created via Hype and then clipped to our area of interest. And all of them are the VH polarization, since that's the polarization we'll be using in this analysis. So if you want to look at any of these RTCs individually, you can also right-click on them and then download them to your local computer, where you can open them in ArcGIS, ArcPro, or QGIS, whichever GIS application is your favorite. Okay, so it looks like we're done unzipping the data. So that is our RTC data. Now, there are also a few other data sets that we'll need in order to do our analysis. And in particular, because landslides are so terrain dependent and slope dependent, it's also very useful to have DEM information that we can use to constrain where we think landslides will be. In particular, if you think about the way that we're actually trying to detect landslides, what we're trying to do is detect basically the removal of vegetation. And there are other processes that can also remove vegetation. So in particular, this removal of vegetation isn't a perfect proxy for landslides, but it is a pretty good one. However, things like agricultural activities can easily create a signature like the one that we see for landslides. So for this analysis, one thing that we do is try and remove areas from the analysis that where agriculture might occur, but where we don't expect landslides to occur. So in particular, what this means is we will be removing flat areas of Haiti from our analysis. So we'll download a DEM, calculate a slope raster based on that DEM, and say for anywhere with a slope that is below, I believe, 3 degrees, we will say that landslides are not likely to occur in these areas, and any log differencing results that we see in this area that could be landslides will throw out, because we're assuming that landslides aren't going to occur in areas that are that flat. So in order to do this, we have a code cell where we'll use the DEM Stitcher package to download and then clip the DEM to our area of interest. Okay, so that has downloaded. And the next thing is we'll just translate it into the same coordinate reference system as our own data, and then also create a slope raster for it, also using GDAL, the geodata extraction library. Okay, and then the next thing that we'll do is, this isn't necessary for the analysis, but it's also just a nice visualization tool, is we'll also download some optical imagery data for the region so that we can visually compare our results to what we're seeing in Sentinel-2 imagery. So we've also stashed some relevant data in S3 for this, these 2 Haiti images. And then we'll also, once we've downloaded those images, reproject them to our area of interest and crop them to our area of interest as well. So at this point, now we have all the data we need. And the next thing we need to do is load all of our data in and then create those pre and post-event images for us to look at. And in order to do this, I want to introduce some Python modules that are very helpful for doing these types of large analyses. And these are the tools Xarray and Dask. So Xarray, let's start off. If you want to read more about it, you can click this link in the notebook, and it will take you to the documentation for Xarray. And Xarray is useful for us is because it is a Python library that makes it easy to view stacks of data. Normally images that we would analyze in Python have 2 dimensions, an X dimension and a Y dimension. However, for our data here, we have multiple dimensions. We have our normal X and Y, but then we're also trying to do analyses through a time dimension or a 3rd dimension. And Xarray does a really good job of helping us keep track of all these different dimensions that we're working along, and then allows us to easily work in the native units of the dimensions that we're using. So for instance, if you use NumPy, which is another tool for working with arrays in Python, you have to work with integer indexes. So you might have image 0, 1, 2, 3, 4, 5. And this is sometimes frustrating if you really want those 0, 1, 2, 3, 4, 5s. We instead want to think about time instead of these just integer indexes. And Xarray allows us to basically say, okay, this is the image for March 1st, 2020. And that makes it a lot easier to understand the code that we're writing for doing these types of time series analyses, and makes us less likely to make mistakes. Another great feature of Xarray is that it integrates really well with Dask to support parallel computing. Now and this is really helpful because for the types of analyses that we're doing, we often will have pixel-wise operations. And what will happen is basically we'll take the average of each pixel in an image through the time dimension. And so that'll be, say, like 100,000 calculations of an average. And those are completely independent calculations. And what Dask allows us to do is actually leverage the fact that our computers have multiple cores and do some of those average calculations on one part of the core, and then other average calculations on another part. In addition, if we're working with more imagery that can easily fit into the memory of our computer, Dask will allow us to load just a bit of the analysis into memory at a time, and then run that calculation and write that to disk, and then load the next set of data into memory, and then write that to disk. And this is very helpful because there have been, many points in different analyses that I've done where you run into these dreaded out of memory errors, where you get halfway through a longer analysis, and all of a sudden your computer crashes because you don't have enough memory to actually run your analysis. And when you use Dask and Xarray together, it's a great way to do very large analyses without ever running into these out of memory errors. So the first thing that we will do in order to get these images into an Xarray format is define a simple function for pre-processing our data that basically just associates the correct time with each image based on a file name. And then the workhorse here is, we're basically grabbing all the vh-clipped.tiff files in this directory, which I showed you earlier. If you see here, each file ends in this vh_clip.tiff extension, which we're doing a simple search for here in this line. And then we're then using Xarray, abbreviated here as XR, and then the open mf dataset call to actually turn all these images into a time series stack. So we'll let that run just a little bit. And so now we have our images loaded in, and let's take a look at what we have. So this is another very cool feature of Xarray. When you're working in notebooks, and you basically make a call to your time series stack, it will print out a nice little formatted example of showing you what exactly we're working with. And in this case, we have lots of interesting information. So we see that we're working with the VH band of our data. We have 34 steps in the time domain, which basically means we have images from 34 different time periods. Our Y dimension has 11,000 pixels tall, and our X dimension is 14,000 pixels wide. And here we can see that the actual total bytes of this array is 20 gigabytes. And this is where the out of memory errors start to creep in, like I was mentioning earlier. I believe that the instances we're working on here in OpenSAR Lab don't have 20 gigabytes of storage available memory available to them. And because of that, if we try to load this entire data set into Python using a tool like NumPy, basically this notebook would have crashed immediately because we don't have that much space. But what Xarray allows us to do is instead load the data set in one chunk at a time. And these chunks are only about 130 megabytes at a time. And this allows us to easily, run our analyses for one piece of the image, one piece of the stack at a time. And here's just, some additional information about each dimension of our time series stack. If you want to see more information about it, in particular, if you want to look at, what time periods we have represented in this stack, you can click on this little button here by the time dimension, and it will show you a drop-down list of what actual time periods are available in our time series stack. Yeah, and just while we're paused here, I just want to iterate how much I love Xarray. I was made aware of it about 2 or 3 years ago, and I try to use it now whenever I can. It's a really nice way to really understand the data that you're working with, and then work with very large data sets inside of Python environments. So yeah, really recommend using it whenever you can. So the next thing we'll do is, this stack of images that is represented here actually represent the whole scene available for our RTC. And if we scroll back up to the top of our notebook, I just want to remind you guys that actually our scene covers much more area than we actually want to run our analysis for. You know, large parts of this scene are actually over the ocean, and there are not going to be landslides that we care about in the ocean. So what we would like to do is to actually constrain our analysis to this part of Haiti where we actually expect these landslides to be. And another nice thing about X-ray is it allows us to basically start easily do these types of subsetting analyses without loading all of the data into memory. So we define our slices, and these are just coordinates in a UTM coordinate system. And then now if we take another look at our time series stack, we'll see that now the X and Y dimensions are much smaller. You know, we went from having, I believe, what was it, roughly 11,000 pixels in the Y dimension and 14,000 in the X. Now we have about 4,000 in the Y dimension and 7,000 in the X. So we're starting to constrain the actual analysis we're doing to our area of interest. And you can see, once again, we have the same number of time steps because we're still interested in having data for all the time periods, just in a smaller area. So the next thing we're going to do is convert our RTCs to the decibel scale. And this is the when you hear a log difference analysis phrase, this is basically the log component. We're taking the log of the VH values here so that they scale more nicely and we can more easily do difference analyses between the two time series that we're looking at. So another important thing to always remember about X-ray is that it actually delays its computation. So this little piece of code right here will tell this notebook, hey, tell me how much time it took to run this notebook. And what you'll see is that it runs very quickly, much quickly than you would assume it would take to make this type of calculation for a very large area of an image. And that's because basically we're giving X-ray a set of instructions that it will at a later time actually execute for this image tag. And the reason that it does this is that sometimes there are ways to better optimize the order in which certain calculations are done to speed up the processing time. So when we run this, we'll see that, you know, it only took 4.9 milliseconds to run this cell because we're basically just collecting sets of instructions at this time. We're not actually running anything. So now that we've calculated the log or converted to a decibel scale for our RTCs, we'll then create temporal averages for the pre-event section of our time series stack and the post-event section. And if you want to get a refresher of what this is going to look like, we can scroll back up to the top of the notebook here. So what we're going to be doing is taking the temporal average of all of these scenes before the image, and then a second temporal average of these three scenes after the event has occurred. Scrolled a little too far. Here we go. So once again, here's our start, end, and event times. And then we're going to basically group by whether or not you are pre-event or post-event. And then take the median value here. That should be median. That's just a little bit of a mistake on my end. But we're going to be basically taking the temporal median before the earthquake occurred and the temporal median after the earthquake occurred. And once again, you'll see that that cell completed very quickly because we're really just creating a set of instructions that we're going to run later. And when we look at this, you'll see that our dimensions have changed once again. So because we took the averages for the two different time periods, post-event or pre-event and post-event, instead of having 34 different time steps, no, we now just have 2, the pre-event and the post-event. But we still have the same Y and X spatial dimensions because we've averaged through time, but not over space. Okay. And then, so now that we've done this for each image, we're now going to mask out areas where the slopes are less than 5%. This was the step I was alluding to earlier when I was talking about the DEM. Basically, we're assuming that landslides are not going to occur in areas where the slope is less than 5 degrees, which is a very reasonable assumption, and also an assumption that Handwerker et al. Made in their paper analyzing this data. So here we'll just load our slope file, this slope.tif, into X-ray, and then create a slope mask, where basically the mask is equal to true, where the slope is greater than 5% and equal to false, where it's less than 5%. So this is computed and loaded in. And then now we're basically going to subset our time series data and just mask out any areas that are have a slope of less than 5%. Okay, so now we have 2 images, a pre-event and a post-event image, and areas where either of them have a slope of less than 5% has been masked out. Now we can actually perform the log difference, which is as simple as actually just subtracting one of these from the other, now that we've already converted them to a log scale. And this is the step where we'll actually run our computation. And you can tell that because we have a call here to the .compute method. And this is the method actually tells Xarray and Dask, okay, now actually run all these calculations that you've been collecting. And so this, I believe, will take a little bit of time, and you'll get some information report to the screen. Yeah, we'll just wait for this to run. And this will be another time where we can pause and check in on anybody who has any issues while this runs. As an aside, in my own work, I was more focused on the slow moving creeping landslides that I discussed at the beginning of this notebook tutorial. And in that case, you can use a technique called NISAR to actually track their motion. If you're interested in learning about NISAR, I'd suggest checking out the YouTube recordings that we posted of our previous workshop we held for you all. It's a very interesting technique that you can use to track very slow types of deformation. And increasingly, people have been starting to use it to track slow-moving landslide motion. And slow-moving landslides are very interesting because often they'll move so slow that some people may not even realize that they are occurring. And this can be a huge problem because people will often build roads and other types of infrastructure along or across them. And so in my PhD, we had a scenario where we had identified a couple landslides that were actively moving, and there were several roads and railroads cutting across them. And both the road commissions and the railroad commissions were having quite the time with these features. And basically, they were rebuilding the roads every couple of years and having to regrade them all the time because the land was slowly moving underneath them as they were trying to build these roads. It was a really interesting scenario, and it was cool to be able to see it in the SAR remote sensing data that we were using. So it looks like our calculation is complete. And that took about 1 minute and 5 seconds. So, not overly long, but a little bit longer. So now that we've done all this, let's actually take a look at our results. So this cell will create a little interactive map that you can use to explore. And so in this map here, we have Haiti with the Y dimension and the X dimension. And then here, let me just expand my window a little bit. Yep, that looks a little bit better. Alex, just FYI, I think he was talking about the YouTube videos for our previous workshops that we did.
Okay, I'll stick those in the chat.
Yeah. So this This map is also interactive, so you can use these little tools on the side to navigate around. You can use this 4-arrow tool to actually pan. And then you can use this little square tool to zoom in on particular areas. And what you do is you click down, drag out a little box, and then you'll zoom in. And you can look in greater detail on the data. And then this home button will return you to the data resolution. So for instance, here's an area. Actually, I think this is another good time to pause and ask you guys a little bit of a question. So for this analysis, we've taken used some VH imagery, calculated our pre-event and post-event images, and then we've subtracted our post-event image from our pre-event image. Now, assuming that VH imagery has more scat or appears brighter or has larger values in the presence of vegetation, would we expect the presence of landslides to have a positive value in our log difference image, or would we expect the presence of landslides to have a negative value? I'll give you guys a little bit of a chance to kind of think through that one, and then also post your guesses in the chat. And yeah, the person who said positive is correct in this case, because we're subtracting our post-event image from our pre-event, and we expect our VH images to be brighter in the presence of vegetation, and landslides remove vegetation when they fail. We would expect our images to have our log difference images to have a positive value in the case where a landslide has occurred. And if we zoom in to this area of our image, we can see areas with a decent amount of bright red. And this is an area where we expect a larger amount of landsliding occurred. Now, I think one thing that you all will notice right away too on this image is that really, if you zoom out to the level of all of Haiti, it's really not super clear, where the landslides are occurring and where they're not. These landslides are typically on the scale of 10 or maybe even 10 to 100 meters across, and maybe 100 to 300 meters long. And the pixel resolutions that we're working with here are 40 meters. So the data that we're working with is relatively coarse for the type of analysis we want to do. And we would love to have high resolution data, but this is just what happens to be publicly available. I know that some disaster agencies will actually buy commercial data that comes at higher resolutions when they need to do these types of disaster responses. But for us researchers working with open data, this is what we have to work with. And in this case, the results can be kind of noisy just because our resolution is about the size of the features that we are actually trying to detect. And so just like our water analysis, what we'll do is, instead of looking at these large images with just this gradient from blue to red, we'll actually try and create a threshold that will help us identify where the landslides are occurring. So I think this, So here is just a zoom in of an area where some landslides seem to have occurred, and a histogram of the values. And here we see a relatively normal distribution between -6 and 6, with some landslides that look like they're occurring up here in red at the top of the image. And this gives us the clue that this thresholding is going to be difficult to conduct, because there isn't a clear separation like there is for water between watered areas and non-watered areas. And in particular, what was used in Hanover et al.'s paper, and what we're going to use here, is basically a manual approach for selecting an appropriate threshold value for where landslides occurred and where they did not. So once again, here's just another plot of our area of interest. And here is a plot where we can actually select a a threshold for what we think constitutes landslide occurrences versus non-landslide occurrences. And here we've selected a threshold value of 2.5. And this corresponds to 2.5 in this map right here. And we're going to assume that, okay, this is probably a relatively good threshold that helps us discriminate landslides for non-landslides, but we can check our assumption by looking at a plot here. So here is one of our Sentinel-1 images. And on top of that, we have overlaid a map of where we expect landslides to be present. Now, at this scale, it's a bit difficult to see, but if we use the zoom in features of these plots, we can see these very bright areas along the sides of the hill. And we can see our little red areas where we believe there to be landslides to be overlaid on top. And so all of these little structures in here or white are where we expect landslides to occur. So it looks like we're doing a decent job. You know, it's not incredible, but it looks like there is information in our analysis. Now, one thing you could do if you feel like, you know, well, I think we could do better than that. I think we could pick a better threshold. You know, you could change this value. Say you want to be a little more strict about what you want to consider a landslide. We could set that value to 3.5 instead of 2.5. And then when you zoom in to this area, zoom in to this area again, you know, we can see that there are many fewer landslide little red pixels identified, but it seems like we've also removed a lot of the most erroneous points. You know, there were many areas up in this section that we had falsely identified as landslides before. You know, in our case, I think I'm going to move ahead with the first 2.5 value, but go ahead and take some time messing with these values if you want to as well. Now, you know, here's another interesting to note. If you look at this Sentinel-2 imagery, the first thing that you'll notice is that there are a significant number of areas with cloud cover. And even though this is a image several, I believe, like about 2 months after this earthquake occurred, this is one of the first images that actually didn't have cloud cover over the entire scene. And so this is the one we're using as our base imagery. But you can tell how, you know, if you're trying to detect landslide activity in these areas post this earthquake, using the optical imagery could become very challenging because, for instance, in this area where we have, you know, significant cloud cover, our SAR analysis is still able to do some landslide detection that would just be impossible with the optical data. So now we've selected, we have pixels that now represent where we think landslides are occurring. However, if you want to pass this data off to some disaster management professional, this isn't the most useful way that you could present the data to them. In particular, you know, they don't really need to know in particular where every single individual landslides are. They're probably looking for broader scale information. In particular, when we've worked with disaster agencies before, what they often are concerned with is where is the landsliding the worst? Where did the most landslides occur? Where are the hot spots where we expect the most damage to be? And so in this case, we can present the data in a way that's a little bit more tailored for what they want to do with it, and actually move from this landslide identification raster to an actual heat map of where we think the density of the landslides is the highest. And so this is what we'll be creating in this final density plot. So what we'll first do is use some other Python packages, in particular the SciPy package, to create a density raster that we will then reproject into the dimensions of our landslide identification imagery, and then we'll plot that just like some of our other data. So we'll first run the density plot calculation, which, you know, this is a little bit of a longer computation as well, but not too long, about 9 seconds. And then we'll go ahead and create some DEM, also threshold that that density raster by that 5% slope value that we used for our log difference analysis. And then we can make our final plot of landslide density following our analysis. And so here is our final plot. This red area is where landslide density is the highest, and this green areas are where the landslide density is low or non-existent. And so what you see here is, if you're handing this off to a disaster management agency, you can tell them, okay, this red area is the place where we've seen the most landslide activity. If you're going to send resources and medical personnel into an area, send them here first. You might also direct them, hey, this small peninsula off the end of the island or off the end of Haiti also seems to be having a bit of higher landslide occurrence. So make sure you take a look there as well. And one thing that's very interesting is actually these landslides are occurring pretty far away from the epicenter of where this earthquake actually occurred. And this happens for a couple of reasons. The first is that there's the mountains are much steeper in this region of Haiti than over here. So there's more potential for landslides to occur just because the slopes are steeper and the same amount of shaking is more likely to produce earthquakes. The second factor that I believe has been explored in some papers concerning the earthquakes occurred after this landslide is that the rocks in this area tend to be a little bit stronger, tend to form more plastically. And in this case, that means that they're transferring the earthquake shaking much more strongly than the rocks in these locations of Haiti did. So, you're getting stronger shaking due to the rock composition, and there are steeper slopes in this area, which are both leading to the occurrence of more landslides. And finally, just to show you that, yes, the analyses that we're doing here are, publication worthy and are really, top end analyses for these types of SAR. Here's the figure, we have created solely off of our analysis. And here is a very similar figure produced by Handwerker et al. That has actually been published in their paper. And you can see that the area where they identified with very high density of landslide occurrences is very similar to the one that we have here. Now, the algorithm that we use to create the density plot is slightly different than theirs. So there are some slight differences in these plots, but you can see that, basically the information that we would be handing off to a disaster management agency is very similar to the one that Handwerker et al.'s analysis produced. And I think this concludes the main part of this notebook tutorial. Now, I imagine that it might take you all a little bit longer to run through this notebook that we did, so I think we'll just hang out here for a little bit. I am happy to answer any questions that you guys have about these analyses in chat while you all work on running this notebook all the way through. So we have a question in chat about estimating 3D velocity. So a couple things to talk about when we want to talk about three-dimensional velocity measurements. The first is that the type of analysis that we ran through today will not be able to get you any type of velocity measurement. Basically, what we're doing here is we're measuring the presence or absence of landslide activity. And because these are the types of landslides that move so quickly that we don't have imagery that actually captures the movement as it's occurring. We won't be able to capture the velocity with this type of analysis. However, as I was mentioning earlier, most of my work around landslides has been done with NISAR time series analyses with slower moving landslides. And in this case, it is actually possible to track their velocity. And in this case, time series velocity can get you most of the way there, but not all the way there to 3D velocity, except for in some more bespoke circumstances. So an important thing to always remember about NISAR, and this is something we covered quite a bit in the previous workshop, is that NISAR is able to measure movement, but only along the direction in which the landslide, or the direction in which the satellite is looking. So as mentioned earlier today, if we have a satellite moving in this direction, basically front and back, it'll be looking off the left or right along some vector. So some vector like this. And so you're measuring motion along this line right here. Now, if we take data from both ascending and descending orbits of a satellite, basically when the satellite is moving north to south and south to north over an area, we can get two different vectors that we're looking along. And we can use those two different vectors to get a sense of motion in several directions. For most polar orbiting satellites, which Sentinel-1 and NISAR are all polar orbiting, we can use the information from these two, line of sight measurements of velocity to make an estimate of what our vertical motion is, basically how much are we moving up and down, and then an estimate of left to right or east to west. But just the way the math works is that if you want to get 3D velocity, this can be very difficult for landslides, because basically in order to accurately estimate a 3D motion, you need to measure that motion along at least three different vectors. And in the case of most NISAR time series analyses, we only have two vectors. So we can resolve the vertical and east-west motion, but we can't resolve the north-south motion in particular. So there are some ways in which you can overcome this, but it kind of depends on your use case. So the first way you can overcome this is just have a satellite fly in a higher number of different directions and take observations along those directions. This isn't commonly done for satellites, just because changing orbits is very expensive and time consuming. But there are some examples of SAR instruments that are flown on airplanes where they have used they've had the airplane fly in multiple different directions and use this to resolve 3D velocity fields for landslides. If you want to look up the papers about this, I would look up papers that talk about UAV SAR and the Slumgullion landslide. That's where most of this work has been done. I'll just type that into chat so that you have the spelling of it. Another technique that some people will use, although I think a lot of people are skeptical of it, is that if you assume that you know the direction in which the landslide is moving, you can use that information to back out an estimate of what the 3D velocity is of a landslide. And so what people typically assume in this case is that the landslide is moving down slope. So they'll use a DEM to calculate both the angle, the 3D angle that a slope is at a landslide's location, and they'll assume that a landslide is moving along that vector. Now, in real world cases, the motion of landslides is often very complex, and different parts of the landslides will be moving in different directions. So this often is not a good assumption, but it is one option if you want to try to estimate the 3D velocity of a landslide. You know ahead of time that the type of motion your landslide is exhibiting is relatively simple, and basically it is only exhibiting downslope motion. And in that case, you know, you can use that to back out an estimation of the 3D velocity. I know that I was very in-depth answer to that question, but it's something I've thought a lot about. Yeah, there have definitely been times throughout my work where I've really wished I had a better way to resolve the 3D deformation of landslides. So we have another question about landslide. If the landslide is moving either north or south, what will the accuracy of the measurement be? And this is a very good point. So because satellites like Sentinel-1 and NISAR will be polar orbiting, their vectors have a very strong the vectors on which they're measuring motion have a very strong east-west component and a very strong up-down component, but they have a very, very small north-south component. So it makes it very, very difficult to measure any type of north-south motion using Sentinel-1 or NISAR-like satellites. And in particular, we have almost no sensitivity to north-south motion using these satellites. And so what you'll often see in landslide studies that use NISAR is that there can be a bias in the landslides that are identified, because we're only able to really identify landslides that have strong up-down or east-west movement. I believe there are papers and techniques for calculating based on, you know, aspects and slopes, what the likelihood of capturing landslide motion in a particular area is. But yes, in general, our ability to capture landslide motion that's in the north-south direction is significantly less than our ability to detect it in the east-west or up-down cases. All right, how is everybody doing with the notebook? Are we able to, you know, run through the analyses, environments working, everything like that?
Boris, there's a question about if the people wanted to run the other tutorial, which environment they would need.
Alex, I might ask for a little bit of help from you on this question, but I believe the NISAR analysis tutorial, or the NISAR analysis environment that you can build inside of OpenSAR Lab should work for this. Just for those of you who are interested, here is the notebook that he's mentioning. It sits right next to the landslide heat maps tutorial in this repository. I'm just looking at this, see what I say. I believe that if you install the NISAR _analysis environment from the notebook that Alex has already shown us, it will have all of the packages that you need to run this notebook.
Alex is in one of the breakout rooms doing some troubleshooting. So Dylan, did you have any insight on that, or?
Yeah, I believe that Forrest is correct. I think there's a bit at the top of the notebook there that talks about the NISAR analysis environment.
Awesome. Thanks, Dylan. One thing that I did want to mention that is nice about landslide analyses in comparison to the flood mapping that Heidi was showing earlier is one of the things that's very difficult about flood mapping is that flooding tends to be very transient. You know, the signature of flooding does not tend to last or basically the presence of standing water in an area does not need to last very long for, you know, the flooding in the area to have major impacts. So one thing that is very beneficial in the landslide case is that we were able to average together 3 post-event images to basically reduce the amount of noise in our post-event image. Typically, this isn't possible when you're doing flood mapping analyses because, you know, the flooding is so transient that you might have only one image that captures the flooding. And in many cases, you know, the post-event image may not capture even the full extent of flooding because it can grow and contract so quickly. So that's one thing to always try to keep in mind when you're doing these types of like RTC-based analyses. And in general, you could more broadly classify these as RTC change detection analyses. That it's really important to think about how long you expect the signal that you're trying to capture will last on the landscape, because that'll inform, you know, how you craft your analysis. In the landslide case, scars last for a period of probably a couple of months, and still maintain, you know, a very strong signature. And so we're able to average some data after the event occurs to improve our analysis. But a flooding event, you know, that's often not possible. And in some cases with flooding events, you don't even get an image that fully captures the flooding. And so that's something to always keep aware of when you're doing these analyses.
Yes, I'll add on to that. In fact, the images that I used for the use case earlier, those did not capture the maximum flooding. The second acquisition was more than a week after the flood event had occurred, and in most cases, the flood waters had already subsided. And indeed, if you had captured an image sooner afterwards, you'd get a lot more of that saturated soil. So you would expect after a flood that actually there would be higher backscatter overall. But what you saw in Michigan is that there was lower backscatter overall. And what had happened is that a lot of the fields had flooded and then drained, but it left this caked mud on top of everything, which had very low backscatter. So it actually impacted the returns in a way that would be quite different than if the image had been captured directly after the flood event. So it is really important with flooding. You know, flooding can last for minutes even sometimes. And so what you're capturing in the image when it's being acquired sometime after the event, you do have to definitely keep that in mind, especially with flooding.
Yeah, and I think the Michigan case was in particular very difficult because it was because of a dam outburst, right? So that would have been like a set of water that moved super quickly through the landscape and then contracted afterwards.
It's true that the dam breach was caused because of heavy rain, and so there was the pressures. So it was kind of a combination of things. Yeah, so you did have the rain event that was impacting a lot of the soil elsewhere, not just in the dam area, but then also these really very catastrophic events that were very fast. It did not take long to lose that water from the dam.
Yeah, and I think a natural question arises once you know, like, okay, so you have to really think about the timing of imagery. You then have to ask the question, how will I know kind of where in the flooding history did my image occur? And I think one technique that I've seen people use is that if you have stream gauge data for an area near where you are, often that stream gauge data will tell you basically the height of the water or the amount of discharge that was going through a particular area at a given time. And you can compare the time when your image was collected to that stream gauge information to try and get a sense of where you're at. You know, was this taken slightly before the max flooding, at peak flood, or sometime later on?
So it looks like, so Alex is still working with one participant to troubleshoot the analysis, but otherwise I think we are pretty much wrapped up with our content. Are there any final questions or any comments that the participants would like to share? Could stay. Oh, that's true. We do have a number of resources that are listed in the slide deck. And again, the slide deck for today, it covers both yesterday and today. So there's one link for all the slides for both days. And there are lots of links and resources listed throughout the slide deck. refer to those. I see a question so I did the demonstration in ArcGIS Pro. If you're using QGIS, we haven't developed a custom toolbox, but the process that I demonstrated is very easy to do in QGIS as well. It just doesn't have the custom tools, but you can just do a raster calculation. So like the log difference. And if you want a copy of the actual raster calculations that you would use in QGIS, you can send me an email at I'll type that in the chat. You can send me an email, and I do have a slide deck that goes through how you would do these calculations manually. So if you'd rather use QGIS and you want to know what raster calculations you would use, I do have that available. Yes, there are lots of flood mapping workflows out there. One of the key reasons to show the demonstration that I did was just to give a sense of the data set itself, and so that we're getting into the RTC and looking at those pixels specifically. But there are a lot of automated approaches. It can be a little bit tricky to have a very reliable algorithm that can be used anywhere on the world. But there are a lot of approaches that can be used for water mapping. So that this morning's example was just a very simple use case that in some cases, if you need something quick and easy, that's one way to go. But if you're looking at doing a more in-depth analysis, there are certainly other approaches and algorithms that are out there. So it really depends on your use case scenario. Today's demonstration was a very simple use case, but there are a lot of other approaches. Any other questions or comments before we wrap up? Otherwise, we'll stay online. But if people want to drop off and go to bed,
Yes.
we are getting to the end. So.
Okay, we thank you, Forrest, Heidi, Jackie, Dylan. Of course, Alex is of course still working for 4 days. For you also odd days, for us also okay. For is not odd days, odd timings, sorry. And you have to wake up early and then spend a lot of time, and the preparation of slides, actually particularly each slide takes a long time to prepare. Of course, you have already some slides, and nice Jackie slides also very nice with photographs and arrows. Very I think we like it today. Today more, of course, we could see applications. Actually, many participants would like to see how to apply. So many, agriculture, soil moisture, snow mapping, all. I think some open SAR lab, something tools are available. I think more. I think we will see in future how to use snow product, soil moisture product, or something. Okay, we thank you all on behalf of participants. I thank you, of course. Now slowly participants also reducing, and we can say that this some of PhD students are working landslide, some are working soil moisture. Still they are there. And anyhow, this is very interesting to see that how you can Jupyter nodes, how we can teach our students with the Jupyter nodes is very well. And we must appreciate Alaska SAR faculty members to create wonderful Jupyter nodes. And okay. And
thanks so much. Enjoy the rest of your sleep, I guess.
Yeah.
No,
Thanks
we have
everyone
to take.
for attending.
No, we have to take dinner and then go to sleep.
Aha. Okay. Enjoy your dinner.
Okay. See you.
Enjoy
See you.
dinner. Thanks so much.
Thank you.
See you.